Hey everybody, I just want to do a little Orgo review, make sure we're doing okay. A couple pieces from notes that people have been asking, just some common questions I haven't seen. So first of all, when you start looking at those functional groups, as you're looking on there, I had some questions about the R. R just means a carbon chain. So for example, if you had three carbons with hydrogens all around, coming into a C double bond O, O slash H, this whole chain here of just normal carbons, hydrogens, we can actually just replace with an R because really we don't care about any of that. Really, it's not going to majorly change what this particular organic molecule can do. This is the end that, as a carboxylic acid, would go out and react with stuff much more vigorously than this R chain down here. So if you see R or R prime, that just means different carbon chains coming off of your functional group. Another one, we start to look at our our ether. Would be if we got, say, carbons coming up, and then we had our O, and then carbons coming off on this side. This would be we could call this one R group. It's three carbons long. And then we've got our functional group, the O in the middle. And then we've got a different set of carbons. That would be, R prime. So this would be, if we were just thinking about the name 1, 2, 3, that's three carbon chains. So that'd be a propyl group. Prop for three, meat, eat peanuts. If we had two coming off, that'd be an ethyl group coming off the other side. So it's just kind of shorthanding the different carbon chains. Instead of doing all those carbons, we just simplify them down to R's. Isomers are different structures of the same kind of molecular formula. So for example, if we had C5H12, C5 would be pentane. We could just do the straight chain, 1, 2, 3, 4, 5, and then hydrogens all around, which we could shorten to our structural formula, 1, 2, 3, 4, 5, something like that. Or we could draw it a different way. We could do a carbon with 4 carbons all the way around with then hydrogens all the way around. This is the same number of carbons and hydrogens. We would just give this a different name, but these would be isomers of one another. We sometimes call this branching because it looks like there's branches coming off of our tree, if you will. This actually sterically, or in terms of the molecule, gets in its own way a little bit. It's harder to line those up. The less branching you have, the stronger the LDF forces and higher the melting point. We actually loop them around into cyclo structures. If we were to make this cyclopentane, because we've fixed them in a fixed location, remember we got these sigma bonds that can rotate, so even these still have a little bit of rotation, kind of getting their own way. These actually lock them into a ring, and so there's much less interference or less likelihood that they've twisted. And so these actually have our highest boiling point, melting point, when we start to look at our different structures. So these would all be isomers. Now technically this would be a different number of hydrogens because we've kind of connected the ends. This would just be C5H10. So I apologize, this would not actually be an isomer. This is a different kind of compound, but these would be isomers of one another. Cool, let's talk about how we start to name some of these organic molecules. Hopefully you're doing okay on the straight chains, just count up the number of carbons. Now we're going to start adding some functional groups, start sticking stuff on there. So for example, say you had a 4-carbon chain with a chlorine on there. Well, we aren't very creative here in chemistry. We would call this functional group a chloro group. If it was a fluorine, it'd be a fluoro. If it was a bromine, it'd be a bromo group. So we're just saying, what is the kind of special atom on here? Now, again, there would be hydrogens all the way around. If we were looking at the skeletal form, this is 1, 2, 3, 4. You always start by counting your longest chain of carbons. This would be a butane group. And we've got a chlorine coming off of our kind of second carbon here. So if we wanted to name this, according to our IUPAC standard naming kind of functions, we always start by counting the longest chain of carbons, and we start with the carbon closest to your functional group, or whatever will give you the smallest numbers on the functional group. So we got 1, 2, 3, 4 carbons going across. We would say that our chlorine, our special kind of anomaly or functional group here, the chlorine is on the 2 carbons, so we'd call this 2-chloro, to say that this chloro group, this chlorine, is attached to the second carbon on a 1, 2, 3, 4 carbon chain, which would be butane. So this molecule with no miscommunication is called 2-chlorobutane. There's another chlorine here on our kind of skeletal function. It would look like this. We got to see where both of those chlorines are. Well, if this was the 2 carbon, this is the 3 carbon. So this now becomes a 2,3 dichlorobutane. butane, indicating that there's two functional groups on this molecule. We got to show exactly where both of them are, show that there are two of them, and then we give our base name as we did before. If they were different functional groups, again, as chemists, we're not particularly creative. This would be a chloro group. This would be a bromo group. We would actually argue we're going to number from the side that is a little more reactive. I would not worry about that quite yet. But we would actually flip this so that our bromo, alphabetically, bromo, B before C, our bromo has the lower number. You could argue either direction here in terms of the nomenclature, and I would take both. But now we've got a 2-bromo. It comes first because B is before C. And then 3-chloro, and it's still a 4-carbon chain, butane. So 2-bromo, 3-chloro, butane. If one of these was, say, a methyl group, CH3 coming off of here. So this would be CH3. Our longest chain is still 1, 2, 3, 4. Ooh, but we wouldn't number this way because we want our numbers to start closest to the special group that's attached. And so we would start 1, 2, 3, 4 going across. Here, I'll add another carbon just for sake of practice here. Now I've got a 5-carbon chain as our longest chain. So I start by finding your longest chain, number from the side closest to the functional group, and then name your extra parts. Well, this would be a methane, right? If it was like CH4, but it's not, it's attached. So we actually, again, not super creative, we would call this a methyl group. So this is 2-methyl, and it's a 5-carbon chain, so it'd be pentane. 2-methyl pentane to show that longest group. Cool. Let's say we had the CH2 and this is a CH3. Let's say this was our molecule. Sorry, we got all these kind of hydrogens coming out. I'm not putting the hydrogens for sake of time here. Say this was our functional group coming off of here. We wouldn't need another hydrogen coming off here, sorry. What would you name this one? Well, this is now an ethyl group, right? So it would be 1, 2, 3, 4, 5. So this is the 2 position. This would be 2-ethyl pentane. Always start by finding your longest chain. Our longest chain has changed now. We've got 1, 2, 3, 4, 5, 6 is our longest continuous chain of carbons. So this is now a hexane. And we've got on the 3-carbon methyl group. So this would be 3-methyl hexane. 3-methyl hexane. Cool. Let's practice one from a skeletal form, just because I think it'd be good practice for us to see a slightly different format of this. So let's say our molecule was something that looked like, I'm going to make this one kind of mean. Let's do a chlorine and a bromine on that one. Cool. So let's say this was our skeletal form. Sorry, this line got a little faint. Remember, in our skeletal form, anytime there's an end of a line, that's a carbon. So we've got 1, 2, 3. We could go 4, but I think our longer chain is 4, 5, 6. I started on this end because it was closest to these funky functional groups. This here represents another CH3 coming off, another carbon with enough hydrogens to make it stable. And so we've got 2-bromo, 2-chloro, 3-methyl. Oh, spelled wrong. Methyl. And then it's a 6-carbon chain. Hexane. Seems like a long name, but it's set up in such a way that it is going to be from start to finish. We know exactly where every single piece is, because theoretically, I should be able to give you this, the name of 2-bromo, 2-chloro, 3-methyl hexane, and you'd be able to then draw the structural formula. You know exactly where each and every functional group is because of our numbering system. Cool. Yeah, why don't we try one of those? Let's do 4-chloro, 2-ethyl peptane. Now this is going to be player's choice. If you want to do kind of the structural form, that's fine. If you want to do skeletal, that's fine. As long as you have the right number of carbons, it's going to be okay. We assume there's enough hydrogens to make things stable. Always start with your base. We got heptane, that's 7. I'm going to do skeletal and structural 1, 2, 3, 4, 5, 6, 7 to confirm. 1, 2, 3, 4, 5, 6, 7. Cool. If it helps you, you can always number them. 1, 2, 3, 4. I'm going to stop at 4 because I know it's got all 7. I only need through 4. 4 chloro. So there's going to be a chlorine attached here. 2 ethyl. 1, 2. Oh no! This name's bad. Why? Because my longest chain is not actually a heptane. Sorry, this is a bad example. Let's make this. Oh, that was bad. Sorry, I'm shooting off the cuff here. Yeah, let's go ahead and name it correctly then. Ethyl will be 2 carbon chains, so 1, 2 carbons coming off there. But that then means that my longest chain is actually 1, 2, 3, 4, 5, 6, 7, 8. So the better name here is actually going to be. Looks like 3 methyl and 5 chloro. Alphabetically, the chloro comes first. 5 chloro, 3 methyl, and 8 is octane. Cool. You'll see some questions like this where it's like, okay, here's a name, but it's not the best name. Give us the best name. So based on that example, this would actually be the better name for this molecule. Cool. Lots of different ways you can start to do this. We're going to have some practice coming your way with just kind of naming and writing and drawing these types of structures. If you got questions, let me know. There's a bunch of examples in the PowerPoint as well as on the homework coming your way. Cool.